With just a reminder of what a log is and just the ordering of it. It's a way of expressing an exponent. When I say log base 3 of 9 equals 2, that means the same thing as saying 3 to the second is 9. Just rearranging the order. And you practiced that today, I know, on the quiz you took. Rearranging. If you say log without a subscript, it's understood to be a base 10. So this is 10 to the second equals 100. 10 to the second is 100. And that can be done directly on your calculator. The calculator has a base 10 understood when you say LOG. So log 100, hit the buttons, it should say equals 2 exactly. Your calculator also has an LN button, which is an understood E base. E is a constant, it's approximately 2.7. So when we hit LN of 7, that equals, and you can feel free to follow along on your calculator. Check this out. That means E raised to that power, which is just about 2, E to the almost 2 equals 7. You can check that on your calculator. E to the 1.946 is approximately, I squiggled my lines because it's not exactly if you have to round in it, so it's approximately 7. All right, we're going to use this in today's lesson, so this will be helpful to us. E, understood as the subscript. When you hit ln of E raised to the first equals E. You are rewriting this, the understood E subscript, E to the first is E. So in today's lesson, there's going to be an application we're going to use when we do half-lives in the 4-6 work, where we'll ask you to find how long it takes to deteriorate to half of what you started with, half-life problems. We'll be using this ln of E in that calculation a lot, and it's real handy if you just know. Anytime I see ln E, it's 1. So it kind of just drops out, or 1 multiplier. But this is the reason, because E raised to the first is E. Okay, another example. ln subscript 2 base 2 of 8 would be 3 because 2 to the third is 8. ln base 2 of 7, I left that one blank. This one I can't do directly on my calculator, and I can't just say 2 to what power is 7 since it doesn't come out perfect like some of the other examples. So you use this rule today, but I wanted to remind you the change of base theorem says if it's not base 10, it's not base E, where you can directly hit your calculator, you do this. ln or any base log, it would work, but you only have the 2 handy buttons. ln or the LOG, both will work though. You take the log of the argument, log of 7, divided by the log of the subscript 2. That ratio will give you your answer. So check that out. 2 raised to that 2.81 answer should be 7. So one more time, if we were doing the ln of base 3 of 25. I don't know exactly 3 to what power would be 25. I can give you an estimate, but to get an exact answer, I need this change of base theorem. So I would take the log, LOG, or LN of that ratio. Log of 25 divided by log of 3. Divide that out, that should be your correct answer. Sometimes you need to close a parenthesis. If your calculator throws a parenthesis up here, you'll need to tell it to close that before you hit divide, so just watch little things like that. Practice that on your calculators. Okay, the next concept I want to move you to before we get into the 4-5 solving equations. The rules, the log rules say if you have a log of 2 things multiplied together, you can expand that to addition. So condensed log, the log of 2 multiplied, would expand to that same base log, so E is understood, of the 2 plus the 7. Check this out on your calculator. If you do the log of 14 or the ln of 14 directly on your calculator, hit that if you've got your calculator. Verify you get 2.64. If you do it in this rule way, you do the log of 2 plus the log of 7. Practice that, see if you get the same answer. A second. Okay. All right, so I wanted you to see that rule is just absolutely, it works. It's not just an algebraic rule where we were just doing our homework, just that pretending it worked. It really works in real numbers, and you can see that. Another example, the ln of a number that's raised to a power. Now you could just directly put on your calculator, I want you to do this, the ln of 8, 2 to the third is 8, so you could directly just work that problem. And it should be 2.079. With our rules, it says, and this is the big one we're working towards in today's lesson, if you have an exponent on your logarithm problem, the exponent can come down as a multiplier. And that's going to be powerful for solving equations today, because we've solved all types of equations in this class at this point, but we've never solved an equation where the exponent was a variable. So we're going to need the power of this rule to allow us to take the exponent, the variable exponent, bring it down where we can work with it on the level of regular algebra problems we're used to. So this property is going to let us do that. Exponent multiplier. So notice that 3 multiplied by ln of 2, if you type it in this way on your calculator, you should get the same result. The rule works either way. The next rule is the log. And I could use log or ln. The log rules are the same rules, whatever base you're dealing with. When I say ln, it means I'm doing a base e log. So it's still a logarithm. It's a natural logarithm. All the rules apply to all the logs of all different bases. So the log of a division problem, a division can be expanded to, say, subtract. The log of the 8 minus, because it's division, the log of 2. You can check that out as well. If you just did the log of 4, the log of 4 should be 1.39. You do it in expanded form, you get the same result. And then you hit this in your homework some too, where it had a radical around some algebra. So you can do just ln of square root of 25. Type that in directly on your calculator, the ln of the square root of 25 or the ln of 5, you could just say that, is 1.61. So that would be the easy way to do it, since it's just simplify it first. Using the log rules, just to see the rules in action, if you had the square root of 25, you could consider that to be 25 to the 1/2. And we had to do that on some of your homework because it was algebra, you didn't have a number there, you just had a variable. So we had to convert that to its exponential form. The square root means the same thing as the 1/2 power. And then the rule, the second rule there, the rule we talked about where you have a power, the power becomes a multiplier in the front. All right, that's the big one, like I keep saying. Working up to this rule, this big equation we get to work in a minute. If you have an exponent, exponent is a multiplier. So notice the 1/2 is in front of that times the ln of 25. Type that on your calculator, you see you get the 1.6 as well. All right, so those are our rules that let us solve equations. And so the last lesson today, 4.5, is how do you solve log equations, and then 4.6, some reading problems or applications of that. All right, so solving the equation. This one is in your note packet if you want to follow along. I am going to use some of the notes from the first part of your notebook. This is actually example 4. So it says to solve this logarithmic equation. And it's in expanded form right now. Log base A, but don't let that bother you that it's not a real-time number. It's just a variable. It's not going to affect us. The point is, it doesn't matter what base this is, as long as it's the same base throughout the problem, we're allowed to use these condensing rules. So we can say because this is a subtraction problem, this is in its expanded form, you could condense it back down to a division. Subtract goes with divide. And then on the other side, we have the log of base A. And so this is really nice. If you just get it down to where it's just log of one side, log of the other side, just like with all of our other algebra experiences, as long as we do the same thing to each side or undo the same thing to each side, it keeps the balance. So now we have it condensed to a log of a side and a log of the other side. We can kind of just drop out the logs, undo the logarithms, and write a regular algebra problem. So now we don't have a log problem, right? Now we just have a regular algebra problem. To solve this, I would put this x over 1. And I could cross multiply to solve this, right? Because you have a proportion, the cross product should be equal. So x plus 6 times 1 is x plus 6. X times x plus 2. Distribute. And I'll see that it is a quadratic equation. That tells me that I need to get it equal to 0, so I bring all the terms over to one side, so it'll be x squared minus x plus the 2x is 1x, and the 6 brought over will be minus 6. So a quadratic equation, now it's in standard form. It will factor. I get x plus 3, x minus 2. Set each factor equal to 0, which changes the signs of those two terms. And I have a negative 3 and a positive 2. And then I need to check that out. And it's not a thing to check out. You can make this a real-time base if you wanted to see that this is true. But you can't have the log of a negative number. But I think, well, this one is okay. It would be the log of negative 3 plus 6 would be the log of 3. The log of 3 minus the log of negative 3 plus 2, though, is a negative number. The log of negative 1, you're going to get an error reading right there. When you try to do the log of a negative number, and just type that in if you've got your calculator handy, try doing the log of negative 1, just do a base 10 log, it's a regular log of negative 1, and it will reject you, error some way. All right, so I can't use the negative 3. You know, I thought maybe I could, and then I realized right here and even here I would have had trouble. But on the first one, negative 3 plus 6, I still had a positive number there. So anyway, don't automatically reject negative answers, is what I'm saying. Because if you're plussing it onto something, it may wind up being okay. But anyway, it was not. And then try the 2. 2 plus 6, 2 plus 2, and 2. Check that out. The log of 8 minus the log of 4, is that the same thing as the log of 2? And so you can type that in your calculator and make sure that is true, and that answer does work out. Now again, don't just assume that it's a positive number that it also works, because if I have x minus something here, even a positive number may dip down to a negative by the time you put it back in for x. So this part, the argument of the log, has to stay positive before it will go on, no matter. So put this x value into it and then see if it's still positive.